Hello everyone.
Hello everyone.
Mm, Okay, so welcome to the live section for this course, Fundamental of Classical Electrodynamics. So I'm Gitanjali. I'm a PMRF scholar from IIT Delhi, and I'm the TA for this course. So as I said before, in each live session, we'll go through the weekly content as well as we'll start solving few problems that is related to the concept that has been taught during this week. So before starting the session, let me ask whether my screen and my voice is audible to everyone or not. If not, let me know. Uh, Okay, so if it is fine from your side, then let us start the session. So in this week, we basically cover what are the quadruple movement. We started with quadruple movement. Then we see what are the properties of a conductor and how the electric will behave inside a conductor and outside a conductor. What is the boundary condition? What is the electrostatic pressure? And afterwards, we have seen what is a capacitor and how to calculate the different parameters for a capacitor. So this is all we have covered in week 7. So today's session will be all about the problems that is related to finding out capacitor or any higher order dipole moment, such as quadruple moment. So we'll cover that. So so let us start then. So first question is it's a simpler one. So it's I think every one of you can calculate easily uh, the answers for the question number one. So if you see the question number one is three parts. In first part, you need to calculate what is the total charge or it's the monopole moment. And in second part, you need to calculate what is the dipole moment. And in the third part, you need to calculate the quadrum- quadruple moment QXS. So charge distribution is given, and as I suggested, so please try to solve the question side by side so that other than the longer question, you can for the shorter one where it's only the conceptual one, start solving it, and I will give you some time to solve the problem, and we'll see whether the answer is correct or not. So first problem, so there are charges Q minus Q plus Q which are placed at uh, along the x direction. One is at uh, x prime minus a by 2 and one is at the origin and the third one is at the plus a by 2. So first question, it's the total charge. That means the monopole movement. So which is easy to find out because charges are already given Q minus to Q plus Q. So the answer will be option 1, right? So total charge is 0, so monopole moment is 0. For the second one, you need to calculate the dipole moment. So please solve it and let me know the answer. And if you see question number 1, the monopole moment is 0. That means uh, it doesn't matter what is the origin of the system, and you can take any origin you want. You can place Q1 as the origin, minus 2Q is present at the origin, or Q is the origin. You will get the same answer for the dipole moment whenever the total charge is 0. So, what will be the answer for the second question? Option 1. Okay. So for B, option 1 is the correct answer. Okay, so let's move to a question option C. So for this case, you need to calculate what is the quadruple moment, QX. So only one component you need to find out. So if you recall, it's a tensor, right? The quadruple moment, it's a tensor. So you need to find out the first matrix element for this tensor. So if you recall the lecture, the tensor is it's written as half p xi prime xj prime minus r prime square delta ij rho r prime dv prime. So this is the quadruple moment representation. For a one-day case, you can just write this is rho r, it is a line charge, or it's a discrete charge distribution. So you can express it in terms of summation of q, and the dv will be dx. So let me calculate for this, and meanwhile, just check whether you have any doubts in any of these steps. Okay. So for qxx, it's half p x prime square delta ij is 1 and r prime square. Rho r you can write it as, so first see what is rho r. So rho r or rho x prime to be exact for one day case. So this is q delta r prime minus x prime. Let's say this is 1 prime plus delta 2 prime plus delta x3 prime. x1, x2, x3 prime is already given. So rho r, this will be q delta r prime plus a by 2 delta r prime plus delta r prime plus minus a by 2. So r prime is nothing but x prime. So let us see what is qxx now. So this will be half integration p x prime square minus x prime square rho r, which is delta x prime plus a by 2 plus delta prime minus a by 2. Dx prime. Now it's easy to solve. This is 2x prime square. So 2 will cancel. You will have x prime square 2 and delta function. We'll see how to simplify the step in the next in the next question. So for this, we'll get q minus a by 2 square. Second one is it will give 0. This is a by 2 square. Okay, so there will be a minus 2 here. Sorry for that. So minus 2. But the integration will be 0, so the answer will not change. Okay, so answer will be option second. So is this clear, the calculation? We'll see in detail for the 2D case. For 1D, it's quite easy. But for the 2D case, you may get confusion while taking x1 prime and x2 prime. We'll see a problem, but for now, whether question number C is it clear to everyone? Okay, so let us move to our next problem. So it's a continuous charge distribution. There is a axially symmetric static charge distribution of the form given rho is rho 0 r0 by r square e to power minus r by r0 cos square phi. The question is asking to find out what is the radial component of dipole moment due to this charge distribution. So it's quite easy. If you remember, if you recall the formula for the dipole moment, so it's easy to find out what will be the answer. So dipole moment, it is nothing but r prime rho r prime dv prime, right? So r prime is r. Let's say it's r. Let us keep it as r prime only. So r prime rho 0 e to power minus r prime by r0 cos square phi, and dv will be r prime square sin theta d theta d phi dr. Now it's easy to solve because you know the what will be the integration limit. So r prime will be from 0 to infinity, right? Not given whether it is bounded or not. So let us say infinity. And theta limit is from 0 to pi as usual, and phi is 0 to 2 pi. So now we have e to power minus r by r0 r prime e to power minus r by r0 cos square phi and theta d theta d phi dr. So r integration, if you see, it will give, just calculate it, r0 square for the r integration, and for the theta integration it's 2, and for the phi integration it's 5. So overall you will get 2 pi rho 0 r0 to 4. Option A. Okay, so let us move to question number 3. It's based on the multiple expansion. So uh, it's so the radial limit, it was not given R0. It's like it's a constant. It's not like it's a limit for the radius, but because in the question the limit was not given, for the sphere you can take whenever the radius is not given, you can take the limit as infinity. If it is given, then you have to take that particular value, but if it is not given, then you can take its infinity. Okay, so for now, let us see what is number 3. So there are 4 point charges. One is q minus q by 2 minus q minus q by 2. These are at the vertices of a square of side A. And there is another charge minus q at the center of the sphere. And it's given Vr is the electrostatic potential at a point P at a distance R much greater than the side of the square from the center of the sphere. So you need to calculate what will be the ratio for V2R versus VR. And it's given R is much greater than A. So that means you can use the multiple expansion and first see what is the dominant term for the multiple expansion. It's like whether the monopole moment is non-zero or whether the dipole moment is non-zero or whether the quadrupole moment is non-zero. Whichever is non-zero, that term will dominate first. So if monopole is non-zero, then monopole will dominate. But if monopole is zero, then you have to see whether dipole is non-zero or not. And if it is dipole is non-zero, then dipole term will dominate. But if dipole is also zero, then in that case the quadrupole will dominate. Okay. So check once. Check whether the dipole moment is zero or not. So finding out the monopole is quite easy. It's the summation of the total charges. So if you can see the monopole moment, it's the summation of the total charge. There is total 5 charges is there. So minus q by 2, q minus q plus q minus q by 2. So this is all zero. So that means monopole is not dominating. Now let us see whether the dipole is zero or not. And because the monopoly is zero, you can take any point as your origin. So let us say minus q is at the origin. So you can find out the location of all the charges. Let us say this will be it. A by 2, A by 2. This is A by minus A by 2, A by 2. This will be minus A by 2. This is A by 2 minus A by 2. So P will be summation of Qk R prime K, right? For K1 to 5. For the fifth charge, it is at the origin, so it won't contribute. Let us see for the first charge, Q, this will be A by 2, xk plus y cap, then minus q by 2 a. Okay, yes, you are right. The dominant term will be the quadrupole. So find out the answer then. Meanwhile, I will solve the text. So this will be minus q by 2. There will be a by 2, x minus x cap plus y cap plus q minus a by 2, a plus y cap, and minus k by 2, k by 2, x cap minus y. So you can clearly see it here. This will cancel with this, and this one, this will cancel with this. So that means the dipole term is 0. So the next dominant term will be the quadrupole then. So what will be the answer then? We'll see what will be the quadrupole for this case. So for now, can you let me know what will be the V2R by VR if the quadrupole movement is dominating? There are four options. Option 1 is 1, option B is half, option C is 1 by 4, and option D is 1 by 8. You don't need to calculate the quadrupole for this. If quadrupole is dominating, you need to recall what is the relation of V with R. So for monopole, it is 1 by R. For dipole, it is 1 by R square. For quadrupole, it is what is the relation? For quadrupole, it's 1 by R cube. So so 1 by, I think you get confused because while calculating, so R to power 5, it was there when we express the cos square theta in terms of, I think, R and R prime. But whatever within the integral of quadrupole moment, so this is all depends on R prime, not R. So that is why only R to power Q will dominate, not R to power 5. So that is why the answer for this case will be 1 by 8. Okay. So is this clear? Okay, so let us move to our next problem. So it's based on conductor. So there is a metal sphere and it's surrounded by a concentric metal cell. So radius is given for the inner metal cell, it's R metal sphere, and for the outer concentric metal cell, the one radius is A, other radius is B. So given that the inner one, it is the charge of Q, but in the outer cell, there is no charge. So charge Q is there, but here there is no charge. So you need to find out what is the surface charge density at the different surface. One is at the metal sphere and other is at the concentric metal shell. Afterwards, you need to find out what is the potential at the center using infinity at the reference point. Okay. So if you recall, it's quite easy to find out what will be the surface charge density because whatever charges you put inside a metal, so it flows to the surface. So no charges resides inside the metal. So that is why we see the electric field. It's zero inside a metal, and the charge will reside at the surface. And because there is Q charge here, so for this metal sphere, what will be the sigma? Sigma will be sigma r. It will be Q by 4 pi r square. So total charge Q divided by the surface area. For the spherical cell, so this will induce minus Q charge here. So this is because if you recall the electric field inside this metal shell, it should be zero, right? So to make the electric field zero, minus Q charge will be induced inside inside the inner surface of the metal shell. So if you look at this black dotted Gaussian surface, here electric field should be zero. So that means total flux is zero. And total flux is nothing but Q enclosed. So let us say, so this is Q charge. Let us say this is QA charge. You don't know what is the amount of induced charge there. So for this, let's say this is QA and Q by epsilon naught is zero. So that is why the total induced charge inside the inner surface of the metal shell, it is minus of Q. So equal amount of negative charge will be induced in the inner surface of this metal shell to make the electric field zero inside the spherical metal shell. And so that is why if you now calculate the surface charge density for this inner surface, sigma small a, so this will be charge by 4 pi a square. And for the outer surface, because the metal shell was neutral before, right? So only the inner one is charge Q. Outer one doesn't have any charge. So it is neutral. So that means total charge should be zero. And because minus Q is induced inside, plus Q should be induced outside to make it as a whole it is neutral. So that is why sigma B should be Q by 4 pi B square. So this is how we can calculate the induced charge at different surface of a conducting concentric sphere. Okay. So we know the surface charge density now. For the second case, we need to find out what is the potential at the center by taking infinity as the reference point. So it's also easy. So potential at zero, that is at the center, is nothing but integration of infinity to zero E dot dr. And the electric field is different in different region. So it's better to take different integration. So infinity to B E3 dr. Then we have B2A, E2, DR, then A2R, E1, DR, plus R20, E0, DR. So E3 will be, what will be the E3? The electric field outside the region. So this is nothing but total charge by epsilon naught if you take the Gauss law. So this will give Q by 4 pi epsilon naught square dr. And E2 is inside this spherical metal shell, which is 0. So this is 0. And E1 is between the metal sphere and the spherical shell. So this will give Q by 4 pi epsilon naught square dr. And inside the metal shell, from R to 0, it's 0. So now it is minus Q by 4 pi epsilon naught. 1 by R square will give minus 1 by R infinity to B plus minus 1 by R A to R. So this will be Q by 4 pi epsilon naught minus 1 by B, sorry, plus 1 by B plus 1 by R minus 1 by A. Okay. So let us move to our next problem. So it's related to question number, I think it's fourth question, right? Question number 4. So the question says now, let us say the outer surface is touched to the grounding wire, which drains off its charge and lowers its potential to 0. Then how is the surface charge density and potential at the center is affected? So if you ground the outer surface, then how the charges will behave, how the surface charge density will change, how the potential will change. So it's given the after grounding, the total charge is draining off. So that means sigma B is 0. So that is why the potential is now infinity to E 0 dr minus A to R 2 by 4 pi epsilon naught R square dr minus R to 0 0 dr. So this will give Q by 4 pi epsilon naught 1 by R minus 1 by A. Okay, so question number 5 is also related to similar to what we have seen in question number 4. So instead of uh, a concentric metal sphere, now we have cavities. So there are two spherical cavities of radius A and B. These are hollowed out from the interior of a neutral conducting sphere of radius R. At the center of each cavity, we have point charges QA and QB. And you need to find out what is the surface charge density sigma A, sigma B, and sigma R. And what is the field outside the conductor and what is the field within the cavity. So, as we've seen before, the cavities, the first cavity has charge QA, second cavity has charge QB. So this QA will induce minus QA charge here and minus QB charge here because to cancel the influence of this charge on the interior of this metal. And because the metal sphere is it's neutral, so the total charge at the outer surface will be QA plus QB. So that is why sigma A it is minus QA by 4 pi A square. Sigma B is minus QB 4 pi B square and sigma R this is QA plus QB 4 pi R square. For the field, you need to find out what is the uh, total charge enclosed in different region. So field outside the conductor. So for the outside conductor, the total charge enclosed will be QA plus QB, right? Because this QA, this will cancel with QB. So that is why total charge enclosed is QA plus QB. So electric field outside is 1 by 4 pi epsilon naught QA plus QB R square R cap for R greater than capital R. For the cavities, the charge enclosed for the first cavity, the charge enclosed is QA. So that is why EA will be QA by 4 pi epsilon naught R square R cap and EB will be QB R cap by 4 pi epsilon naught R square. This is for R between 0 to A. This is for R between 0 to B. Okay, let us move to our next problem. So it's based on a numerical calculation. It's given a parallel plate capacitor with square plates of side 1 meter is separated by a distance 1 micrometer. And this space is filled by a medium of dielectric constant 10. If the charges on the plates are 1 coulomb and minus 1 coulomb, you need to find out what is the voltage across the capacitor. So calculate it and let me know the answer. It's a direct formula based question. If you recall the relation between capacitance and the voltage, then I think it's easy to solve. Option is 11.29, option B is 13.45, option C is 15.67, and option C is 17.89. take epsilon 0, if you don't recall, it is 8.85 into 10 to the minus 12. Option A, it's your correct. Answer will be option A. So C is nothing but epsilon naught A by D. A is 1 meter square, D is given 1 micrometer, epsilon 0 and epsilon r is also given. From this, you can calculate work plate law. So C is nothing but, V is nothing but Q by C. So Q T by ln naught A. And if you put the values, you will get 11.29 kilovolt. Okay, so let us see next question. So it's to calculate the capacitance of a spherical cell. Say spherical cell which is radii A and outer radius B. So for this, what you need to do, you just need to calculate for capacitance, you need to calculate what is the potential difference between these two cells. From potential difference, you can calculate the capacitance. So to calculate it, first let us see what is the electric field, which is quite easy. Electric field in a region A or B, this is nothing but Q by 4 pi epsilon naught R square RK. So from this, we can calculate what is the potential difference. So this will be B2A P dot dl or dr. So Q by 4 pi epsilon naught 1 by r squared dr. So this will give V is Q by 4 pi epsilon naught 1 by r and B2A. So you have now it is Q by 4 pi epsilon naught 1 by A minus 1 by B. So this is the potential difference. Now for to calculate the capacitance, this is nothing but Q by V. So Q by 4 pi epsilon naught. This will give AB minus B. So C will be 4 pi epsilon naught AB all divided by B minus C. Okay, good. I think you have already calculated. So, okay, so let us move to our next problem. I think you can calculate this also. This is there is a cylinder of capacitance L, sorry, length L, and there are two metal cylinder of radius A and radius B. So you have to ignore what is the age effect, and after that, you need to calculate what is the capacitance for unit length. So same case, you need to first calculate what is the electric field, and from electric field you can write the capacitance and voltage, and from that you can calculate what is the capacitance. So for electric field, you can use the Gauss law. It's E dot ds is Q enclosed for the inner surface. So we are considering a region in between the two cylinder. So that is why this will be E dot ds is Q by epsilon naught, and ds will be 2 pi SL, right? So electric field is Q by 2 pi epsilon naught L 1 by S SK. So this is the electric field. For potential, you need to see what is the integration of EDL between the region B and A. A to B, Q by 2 pi epsilon naught L1 by S ds. So 1 by S ds will give lns, which is ln B by A, right? So negative means the potential of inner surface is greater than the potential of outer surface. So V will be VA minus VV, which will be Q by 2 pi epsilon naught L ln B by A. Now VFC is Q by V, which is 2 pi epsilon naught L ln, sorry, will be in the ln B by A. Okay. Okay, so these two questions are from Griffith. Now let us see our next problem. So for this case, if you recall question number second, we calculate what is the monopole moment for this case. It was coming 0, and dipole moment for this case also it was coming 0. Only the quadrupole moment it was non-zero. So we assume that the quadrupole non. We don't assume, actually it's not non-zero, and because of that we use the relation that V is directly proportional to 1 by RQ. For this problem, you need to calculate what is the expression for this quadrupole moment, quadrupole tensor. What is the full tensor representation of this uh, configuration for the quadrupole moment? Okay, so let us solve it in detail. So only this problem I will solve in detail. For the other problem, we'll briefly go through the steps only. Okay. So if you recall, quadrupole moment is Qij is half the xi prime xi prime minus r prime square delta ij rho r dv prime. So to simplify it, instead of writing rho in terms of q or in terms of delta function, we can take Qij is half summation Qk P Rki Rkj minus RK square delta J. Okay. So QK means the kth charge and RK means what is the position of this kth charge, and RKI means the ith component of the kth charge, and RK is the jth component of the kth charge. We have the total charge is 5, so K will run from 1 to 5. So let us find out the charge and its coordinate. So Q1 is the charge Q at the at A by 2, A by 2, 0, Q2 is minus Q by 2 at minus A by 2, A by 2, 0, Q3, Q minus A by 2, minus A by 2, 0, Q4 is minus Q by 2, A by 2, minus A by 2, 0, and Q5 is at minus Q, which is at the origin. So let us first see what is the diagonal element. Is QXX, QYY, and QZZ. So for QXX, it will be a summation over K, QK, 3 XK square. RKI will be, RK and RKJ will be the X component, and we have RK square. So summation K, QK, RK square, you can write it as XK square minus YK square. And because it's a 2D plane, the Z component is 0. So that is why I have taken the Z part. So now the simplification will give half QK 2XK square minus YK square. Okay. And if we see Q5 is at the origin. So all the coordinates are 0. So that means the Q5 won't have any QXX term. So that is why we'll neglect the Q5 term. Let us first calculate the summation first, then we'll add it up to find out the total value of QXX. So for Q1, it will be QK, which is Q, and 2XK will be A by 2, right? XK is A by 2 square minus A by 2 square. So this is Q A square by 4. For Q2, it is minus Q by 2, 2 minus A by 2 square minus A by 2 square. So this will give minus Q by 2, and you have A by 2 square. So this is minus Q A square by 8. Check whether whatever the values I am getting is matching with your calculation or okay. If you are getting any other value, then let me know. For the third choice, it is Q at minus A by 2 and minus A by 2. So you have Q to minus a by 2 square minus a by 2 square, which is similar to what we have seen in Q1. It will give q squared by 4. And for Q4 is minus q by 2 at a by 2 minus a by 2. So minus q by 2 to a by 2 square minus a by 2 square, which will be minus q square by 8. And for Q5 it's 0. So now we can add it up. 2x is half of q square by 4. And there are 2 and q square by 8. And this 2. Overall it will give q square by 8. So this is qx. For qyy, now we'll have half summation k qk. Rk will be y now. So we have 3yk square minus rk square. Rk we can take it as xk square and y square yk square. So this will give 2yk square minus xk square. So the next calculation is similar to what we have seen in qxs. So for each charge, we need to find out what is the contribution to the summation. Then we add it up to find out the total value. So for Q1, this is 2, yk is a by 2 square, and xk is also a by 2. This will give q is square by 4. For Q2, minus q by 2, 2 a by 2 square minus of a by 2 square. This will give minus q is square by 8. For Q3, it is q to yk is a by 2 square and xk is also a by 2 minus a by 2 square. So this will give q a square by 4. And for Q4, it is minus q by 2 to xk is minus a by 2, sorry, yk, and x is a by 2. This is q a square by 8. So qyy, it will be half q square by 4 2 times q square by 8. So this will give q a square by 8. And qz for this will be half summation qk zk square minus rk square. And because zk is 0 for all, because it's in xy plane, so this is 0. So you have half summation qk xk square minus xk square and yk square for k1 to 4. You know the xk, yk for all the part. So Q1, just check, you will get for Q1 it is minus Q a square by 2. For Q2, you will get Q a square by 4. Q3, you will get minus Q a square by 2. And Q4, you will get Q a square by 4. So QJZ will be minus Q square by 4. So this is the diagonal part. And if you check, if you add the diagonal parts, in the first part you will get Q a square by 4. And for QYY, we get Q a square by 8. And for QXS, you get Q a square by 8. So if you add it up, you will see it will give a 0, which is one of the property of the quadruple tensor. So you can easily check that the matrix will be traceless. 41.8 minus Q square by 4, which is 0. Now we'll see what is the off diagonal element. One is QXY, QYZ, and QXZ. Only these three you need to calculate, and other uh, element it's easy to find out because this is a symmetric tensor, so that is why QXI will be QYX. So we can get QYX if we find out QXY. Then from here we can equate it to QZY, and from here we can equate it to QZX. So first let us see QXY. This is summation K 1 to 4 to K P XK, RKI is XK, and RKJ is Y minus RK square delta X. This is 0 because delta XY is 0. So we have half summation 1 to 4 to K P XK Y. So for Q1, the summation part, this summation part will give Q A by 2, A by 2. So this is 3 Q A square by 4. Q2, it will give minus Q by 2. 3 SK is I think minus A by 2. YK is A by 2. So this is 3 Q A square by 8. And Q3 is Q A minus A by 2 minus A. 3 Q square by 8. And for Q4 is minus Q by 2, 3 A by 2 minus A by 2, which is 3 Q square by 8. So QXY will be summation of this. I think this one is 4. Yes. So we have q squared by 4 and so this will give 9 q squared by 8. So now we know qxi, so that means qyx will be qxy 9 q squared by 8. For the other matrix element qx8, the expression will be qk, p, xk, zk, right? And because zk is 0, sorry, I think we were referring to q3. I've corrected this. So for qx8, because the zk component is 0 for all the cases, for all the coordinates, so that is why we'll find this will be 0. Similarly, qyz is also 0. Okay, so now you have the whole matrix x's, qxy, qxz, qyx, qyy, qyz, qzx, qzy, qzz. This is qx squared by 8, 9q is squared by 8, 0, 9q is squared by 9, sorry, q is squared by 8, 0, 0, 0, minus is by 4. So this is what should you should get at the end. So this is how you can calculate the different element of the quadrupole momentum tension. So just follow the steps in detail, and if you calculate it in detail, then it's easy for you to find out the other, like in the question, they may have asked about qxy or qyz. So remember the steps and use it whenever it is required. Okay. So this will cover calculation of the whole matrix. So is this clear? Do we have any doubt in any of the steps? Okay, so if it is clear, then let us move to question number 10. So now we have I think it's a metal sphere of radius r, and this sphere is charge q, which is surrounded by. So the inner one is charge q. It's a metal sphere, and the radius is r, um, and it is surrounded by two concentric metal shells. This one is radius a, this is b, this is c, and this is d. So we need to calculate what is the surface charge density at the different surface, and you need to find out what is the potential at the center of the sphere by taking infinity as the reference point. So let me ask, what will be the surface charge density in the metal sphere? Sigma r. What is the charge? This is Q, right? This will be Q by 4 pi r square. And because of this Q, you will see, let me take a different, you will see charge minus Q will be induced here, then plus Q charge, then minus Q charge, and plus Q charge. So sigma A will be minus Q by 4 pi A square. Sigma B is Q by 4 pi B square. Sigma C is minus Q by 4 pi C square. Sigma D is Q by 4 pi D square. Let us see the potential. So potential is nothing but integration of infinity 0 E dot dl. So infinity to d, and what will be the electric field in this region? So this will be Q by 4 pi epsilon naught r square dr. And between D to C, electric field is 0, and C to, I think, A, sorry, B. And from C to B, in this region, we'll have Q by 4 pi epsilon naught r square dr. And from B to A, this is 0. And from A to R. So here is Q by 4 pi epsilon naught r square dr. And inside the metal sphere, it is 0. So calculated, it's just a simple integration. It will give Q by 4 pi epsilon naught 1 by D 1 by B minus 1 by C 1 by R minus 1 by A. Okay. Okay, so let us move to our next problem. So I need you to find out the answer, calculate it, and let me know which of these following option is correct. So let me read out the question first. There is a hollow conducting spherical cell of inner radius R1 and outer radius R2. And this encloses a charge Q inside, which is located at a distance d less than R1 from the center of the sphere. You need to find out what is the potential at the center of the cell. So let me draw. There is a conducting spherical cell R1, and there is a charge Q at a distance d. You need to find out what is the potential at the center of this cell. First, calculate what will be the induced charge, and from induced charge, you can just use the formula for the potential of the answer. There is a shortcut also. Instead of finding out the electric field in different ways and then taking the integration, you can also you can recall the potential at the inside of a metal sphere. It's equal to the value at the surface, right? So you can take that concept to find out the answer. So you don't need to find the electric field in different region. Just use the concept that the potential inside is equal to the potential at the surface. So for to use that, you need to find out the induced charge first. Then from induced charge, you can calculate the potential. Um, if it is taking time, let me solve it. Um, so if you recall, if charge Q is it's there inside this metal cell, so minus Q will be induced here and plus Q will induce here. Now it's finding the potential is easy because if you see the charge Q, because of the charge Q, what will be the potential at the center is Q by 4 pi epsilon D, right? And for minus Q, which is at the inner surface of this metal cell. So for this, the potential at the center will be equal to the potential at the surface. So that is why you can take this as Q by 4 pi epsilon naught R1. Okay. And for the outer surface also, it's a metal cell and the potential at the center is equal to the potential at the surface. So that is why you can take this as Q by 4 pi epsilon naught R2. So you can see the potential now is 1 by D. Let's keep Q inside minus 1 by R1 plus 1 by R2. Option D. Okay. So let us move to our next problem. So the question says there is a charge q which is uniformly distributed over a cylindrical volume of radius r and height h, centered on the horizon with its axis along the z-axis. And you need to find out what is the quadrupole moment tensor component q, z, z of the system. And the answer is here written in terms of the height h and the radius r. So qij, if we recall, it is integration a xi prime xj prime delta ij r prime square rho r prime dv. For q z z, we have integration a z square r prime square rho r prime, and dv prime for this cylinder will be r d theta dr dz. So it was given the Q is uniformly distributed over the cylindrical volume of radius r. So that means rho r, you can guess it will be Q by V, and V is pi r square h, right? So this is done. Now r prime square, it's like it's the location of the charge element. So for the location of charge element, you can write it as x square plus y square plus z square, right? And x square plus y square, it is nothing but r square in the cylindrical coordinate, r square plus z square. Now we can simplify it, the qzz. This will be half q by pi r square h integration on a z square. Okay, so 3z square, and this is r square plus z square. So this will give 2z square minus r square or dr d theta dz. So d theta will give 2 pi. So this 2 pi will cancel with 2 pi here. So we have 2 r square h integration 2 z square r minus r cube dr dz. Z, it's given the height is h, so and it is centered at the horizon. Cylinder is it is centered at the horizon, so we can take this is minus h by 2 to h by 2. And radius, it is given the cylinder is radius r, so this is 0 to r. We can separate out the integration. To z square r dr dz minus r cube dr dz. 2, Z square will give ZQ by 3, minus H by 2, H by 2, R will give R square by 2, from 0 to R, minus RQ will give outward 4 by 4, from 0 to R, and dz will give Z minus H by 2 to H by 2. So if we simplify it, it will give 2 HR square to R square by 2, 2 by 3, minus H R to 4 by 4. So this will give Q by 12 H square minus 3R square. Option B. So is this problem clear to you? Do you have any doubts in any of the steps? Okay, so if it is clear, calculate the answer for question 13. It's related to one of the questions that we have seen before. So there is a cylindrical cable which is 8 km long. You need to calculate the capacitance for this case. Given the epsilon r is 3.5 and the inner radius is 10 millimeter. This has the thickness of 5 millimeter. The potential of outer surface is 0 and inner one is 1 kilovolt. What will be the potential? Sorry, capacitance. So if you recall, we have seen capacitance is 2 pi epsilon naught L ln B by A, right? So this we have seen before. We have calculated the capacitance by taking uh, the integration of the electric field, then finding out the potential, then from potential we have calculated what will be the capacitance. So the values are given here. For this case, this will be 2 pi epsilon naught L L L B by A. So two 3 point is into 3.14. Epsilon naught is 8.85 times 12. Epsilon r is given 3.5. And length L is also given. It's 8 kilometer long. 8 into 10 to the 3. Ln B by A. So B is 15, right? This is 15. 15 by 10. So you will get 3.8 microfarad for this case. Okay, so for next problem, it's similar to the question number 13, but here we have uh, two metal spheres, spherical cells. So these are surrounded by a, so like this is a cable and this is one of the cable. So for this case, you need to find out the capacitance for unit length, and this is filled with epsilon 2. This region is filled with epsilon 1. So similar to before, for this inner one, you can write C1 is 2 pi epsilon 1 ln R2 by R1, right? For the outer one, you can write C2 is 2 pi epsilon 2 ln R3 by R2. This is the capacitance for unit length, not the total capacitance. And these are all in series, so that is why you can write the total capacitance for unit length is C1 C2 over C1 plus C2. So this will be 2 pi epsilon 1 epsilon 2 epsilon ln R2 by R1 plus epsilon 1 ln R1 by R2. Okay, so let us move to our next problem. So there is an insulating sphere of radius A. It carries a charge density rho r, which is rho 0 a square minus r square cos theta or r less than a. The leading order term for the electric field at a distance d far away from the charge distribution is proportional. So we need to find out what is the leading order term for the electric field at a larger distance. So it's related to monopole expansion. Sorry, multiple expansion. So I would like, uh, I would request you to find out what is the leading order term. Just check which one is dominating, whether it is monopole or whether it is the dipole which is dominating. Check it and let me know the answer. Let me give you a hint. So first you need to see uh, for the potential which of the term is dominating, whether it is monopole which is dominating or dipole or quadrupole. And if you know the dominating term for the potential, then electric field is nothing but the gradient of potential. So it will add one factor of R there. So first check which the potential which is the dominating factor, dominating moment. Uh, if it is taking time, let me solve it. So monopole moment, it is nothing but the total charge. It is rho r prime dv prime, right? So rho is given. It is rho 0 a square minus r square cos theta, and dv is r square sin theta d theta d phi dr. But if you look at the theta integration, so it has cos theta and sin theta, which is nothing but sin 2 theta. And the sin 2 theta integration between 0 to pi, it will be 0, right? So this is 0. So that is why the monopole term is not dominating. Now let us see the dipole term. So dipole moment, it is r prime rho r cos theta dv. 0 to a, 0 to pi, 0 to 2 pi, r prime rho 0 is square minus r square cos square theta r square sin square theta d theta d phi d. So sin square theta, cos square theta, you can simplify it, and if you see, this won't be 0. So it's like sin square 2 theta, and sin square 2 theta, you can take it as, can write it in terms of cos 4 theta. So from that, you will see it is non-zero, d phi is also non-zero, and r is also non-zero. So that means the dipole moment is non-zero. So for VR, the dominating factor is V dipole. So that means VR will be 1 by r square. And from that, electric field is minus 2v by dou r. So this will be proportional to 1 by r cube. Okay. So 1 by r cube or 1 by d cube. Answer will be option C. So sin square theta, it's in the dv term, right? For the, sorry, it's sin theta, right? Sorry, there was a typo here. R squared sin theta d phi d. So for this case, it's like x square dx cos square theta sin theta d theta, which will give x cube by 3, I guess. Then from 0 to pi, this won't be 0. So that is why it's non-zero. Okay. Any other doubt you have? Let us move to our next question. It's a simpler one. Say parallel plate capacitor with square plates of side 1 meter separated by a distance 1 micrometer. And this is filled with a medium of dielectric constant 10. If the charges on the two plates are 1 coulomb and minus 1 coulomb, you need to find out what is the voltage across the capacitor. So voltage is Q by C, which is Q D by epsilon naught A. And Q is 1 coulomb, D is given 1 micrometer. This is 8.85, 10 areas. So I think we have solved this. This is 11.29. For the 17th question, so there are three charges. One is 2 coulomb, minus 1 coulomb, minus 1 coulomb. These are placed at the vertices of an equilateral triangle of side 1 meter, as shown in the figure. And the component of the electric dipole moment about the marked origin along the y direction. So this is the origin. You need to find out what is the dipole moment component across the y-axis. Solve it and let me know the answer. I think it's better if I solve it first. So P, you can write it as summation of Ri prime Qi, right? So for minus 1 coulomb, you can write it as minus 1 escape, minus 1, 2 escape, plus 2. The location of this is 1.5 escape plus height of this equilateral triangle is root 3 by 2a. So root 3 by 2, a is 1, like. And for x part, the px is, I think it will come out as 6. And for y part, it is 2 root 3 by 2 yk. This is root 3 yk. This is root 3. Now we'll solve our last problem. So it's based on the capacitance. So there is a pair of 200-meter long concentric cylinder, uh, which is radius 50 millimeter and 100 millimeter. And the space is filled with dielectric epsilon is 10 epsilon 0. And a voltage is applied between the conductors to establish an electric field, which is 10 to the 6 by R, RK, between the cylinder. So you need to find out what is the energy stored. So energy stored due to this electric field is nothing but half epsilon naught E square dV, right? So epsilon by 2, we have triple integration. Electric field is 10 to the 6 by R square, and dV for the cylinder is R d phi dr dz. Epsilon by 2, R integration is 10 to the 6 square. 1 R will cancel with R square, so this will give R dr. And the limit for R is 50 millimeter to 100 millimeter. So R is 0.05, 0.1. D phi is 0 to 2 pi, and dz is 0 to 200 millimeter, 0.2. So epsilon naught, epsilon is 10 epsilon naught. So it is 10, 8.85 into 12 by 2. 1 by R will give ln R. So ln 0.1, 0.05. D phi integration is 2 pi, and dz will give 0.2. So this overall will give 38.5 joule. Okay. Okay, so I wanted to solve one more problem, but we'll see in the next lab session. For now, let me ask whether you have any doubt in any of these questions that I've solved. Okay, so if you have no doubt, let us stop for now. Thank you for joining the session. I hope whatever I've solved, it is helpful for you to solve the assignment problem. If not, if you have any doubt, feel free to ask me during the live section or in the discussion forum. So we'll stop for now. We'll meet on next Friday, same time from 6 to 8 to see or to solve few more problems and to clarify your doubts. So thank you for joining this session. Goodbye, everyone.